All right, so we're going to work on factoring polynomials by grouping, page 337. This is in the old polynomial packet, not the new one. So this is just a strategy that's nice to know. You're going to use it when you have 4 terms. It's very similar to the box method. So if you're more comfortable with the box method, I will show you these examples using the box method because I'm going to complete examples 1 and 2, and then you're going to try 3 and 4. And then I'm going to complete examples 5 and 6. So I'm going to save. Actually, I'm going to do 1 and 3 because these are equals and this is just factoring. You are going to try numbers 2 and 4. And I'm going to do 5 and 6 at the bottom. Okay, so example 1. So all grouping is you arrange your polynomial in standard form, and you're going to group together the first 2 terms and the last 2 terms. Now, if there's a negative, that gets grouped in with the 8x, so negative 8x right there. So your next step after you group together the first 2 terms and the last 2 terms, you want to find the greatest common factor for each of your parentheses. So the greatest common factor in the first parentheses is just x squared. When I divide each of these terms by x squared, I get 2x plus 1. So I took x squared out of each of these first 2 terms, and I was left with 2x plus 1. What's the greatest common factor over here? I want to force my next parenthesis to be 2x plus 1. So if I factor out a negative 4 from each of these terms, see how when I do negative 4 taken out, I have 2x plus 1 left inside, dividing both of those by negative 4. See how 2x plus 1 shows up in both places? 2x plus 1 is now the greatest common factor. And then what do you have left? X squared minus 4. Now this can actually be factored one step further because this one is difference of squares. So my final answer would be 2x plus 1, x plus 2, x minus 1. So what would this have looked like using the box instead of grouping? Well, it actually would be maybe easier for some of you, I'm not sure. You're going to arrange these 4 terms inside the box. 2x cubed plus x squared minus 8x minus 4. And you're just going to factor along the outside of the box just like we did with the box method. So I would have x squared times 2, times 2x would give me 2x cubed, 2x times negative 4, x squared times 1, negative 4 times 1. So it all checks out. So see how you get the same factors? 2x plus 1 and x squared minus 4. So factoring by grouping, it's a little bit easier than the box method because you already have all 4 terms to go inside your box. So let's do example 3 together. So in example 3, because it says equal to 0 at the end, so here I could leave it in factored form, but here I really need to take it a step further. So I'm going to show you the strategy by grouping and by box method one more time. If I group these together, I want to pull out the greatest common factor, and that's going to be 2x. And I'll have, it looks like x minus 3 left. I'm dividing by 2x, dividing by 2x. So I have x minus 3 left. Don't you notice x minus 3 is sitting over here? And all I can pull out of that would be a 1. So anything always has a greatest common factor of at least 1. See how the x minus 3's are in both places? That tells you that x minus 3 is your greatest common factor of 2x plus 1. So that is equal to 0 originally. So my two zeros would be that x has to equal 3 or negative 1/2, which comes from these 2 factors. So let's just show what you do one more time for the box method, and then you're going to try 2 and 4. Let's see, 2x squared minus 6x, x, and minus 3. So I'm trying to factor on the outside. So I'd want to put my 2x on this side, positive 1, negative 3. So x minus 3, 2x plus 1. See how the box method gives you the same factors? So you're going to try example 2 and 4 at the end here. I'm going to show you examples 5 and 6. Factor the polynomial and find all roots. So I'm assuming this is going to be factored by grouping. So I can pull out a 3x squared and I'll have x plus 2 left. So I'm dividing this by 3x and I'm dividing this by 3x and I have x plus 2. And over here, I want to force it to be x plus 2 on the inside. So that must mean that I have to take out negative 27 from each of those terms so that I have x plus 2. So I have x plus 2 times 3x squared minus 27. This can actually go further because I should have factored out a greatest common factor before I started of 3. So I'm just going to factor out that greatest common factor now. So I have a 3 as a greatest common factor, which turns this just into x squared minus 9. And then x squared minus 9 is x plus 3 and x minus 3. So it looks like I have 3 roots. X can equal -2, -3, or 3, and they all have odd multiplicity, right? Because they each have the first power. In example 6, they gave me a hint that -1 is a 0, so I'm not sure if this is going to be factorable by grouping. I don't think it is. If -1 is a 0, that tells you that x plus 1 has to be a factor. So we're actually going to take x plus 1, and we're going to do some division here. So I'm taking this and dividing by x plus 1. So 2x cubed would go inside my box. So now what goes on top of the box? 2x squared, right? So 2x squared. Let's see, I want to get a total of 5x squared, so this must be 3x squared, which makes this 3x. And then I want to get a total of 1x. So what has to go in that box so that 3x plus something will give me 1x? It would be -2x. And, oh yeah, it was a factor, right? So I should end up with no remainder. So -2 matches the -2 up here. So I have x plus 1, and then I've got 2x squared plus 3x minus 2 as my other factor. So you should be able to factor this with the box method, right, into 2 binomials. I'm kind of running out of room here. So here's my box method. 2 times -2 is -4, has to add up to 3. 2x squared, -2. I must have to pick +4 and -1. 4x, -1x. Right, you should be able to do the box method hopefully by now. So this looks like it's an x plus 2 and a 2x minus 1. Does that look right? 2x squared, 4x minus 1x, and -2. So my roots are -1 or -2 or 1/2, and they all have multiplicity that's odd, right? First power, first power, first power. So now don't forget to finish 337. You're going to go back and complete examples 2 and 4, and then you're going to move on to 338, the polynomial application problems.